Welcome back. This is one particular concept. I don't really know where I could have infused it. It's kind of a knockoff and a kind of its own. So I figured I'll infuse it into this video, and I'll also wrap up another law in the same video. So determining density of liquids and solids are fairly easier compared to determining density of a gas. What is density? Density is mass over volume, right? Now, if you can control the temperature and the pressure to standard conditions, then you can determine the density of the gas by using the molar mass of the gas. Right? Now, we know standard temperature pressure is 0 degrees, right? Or 273 Kelvin, and 1 atmospheric pressure, right? Now, how do we determine density under these conditions? All you need to do is take the molar mass of the substance and divide it by 22.4 liter. Why 22.4 liter? Because 1 mole of any gas at STP occupies 22.4 liters. Okay, these are the STP conditions. So this is the formula. Again, this probably will be in the appendix. So what is the density of carbon dioxide at STP? So density equals molar mass is grams over mole. Now you could ask me, hey, density is grams over either mils or grams over liter, or you can keep going. But molar mass actually has grams over mole, and if you divide that by liter, hey, what happens to the mole? Remember, it's per mole, right? So you can see it's simply same as writing grams over liter. That's all there is, right? Does that make sense? Why that disappears? Per mole is 1. 1 is not a big deal, so we can ignore that, right? Molar mass of a substance, carbon dioxide is 44 grams over mole over 22.4 liters. So 44 over 22.4 is 1.96 grams over liter. Because this is, again, per mole, so we can get rid of that from the units. And that's how you determine density at STP. Now, it has to be STP, otherwise you cannot use this formula. Okay. Now let's move on to the second law. I believe this is the 4th law in the process. It's Gay-Lussac's law. And Gay-Lussac's law compares pressure and temperature, where number of moles and volume are constant. Again, all of these are derived from the ideal gas law. So N and V are constant. R is always constant, so it's pressure and T. Pressure and temperature are directly proportional. As you can see that, why is that the case? Because again, it relates back to the average kinetic energy. When you heat, particles move faster. When they move faster, they collide faster. When they collide faster, they result in more and more pressure. So you could have technically same volume. I don't know how many of you have cooked with a pressure cooker. Pressure cooker is the most efficient way of saving energy. Okay, so it keeps the volume of the pressure cooker stays the same, but your food goes through under intense pressure because of the heating. So the food cooks faster, and it's actually more efficient way of saving energy, right? So anyways, that's a little side thought I want you to think. So here's a problem. As I said, when you're comparing two variables, if it is temperature, temperature must be converted to Kelvin. But when it's ideal gas law, all terms must be converted to appropriate representations, right? So in this case, pressure do not have to be converted, but temperature must be, right? The gases in a hairspray are at a temperature of 27 degrees Celsius and pressure. So these two go together. So this will be your T1, this will be your P1. And so if the gases in the can reaches a pressure of 90, so that's P2, you're asked to find T2. So all you got to do is convert this 27 degrees Celsius to Kelvin, which would be 300 Kelvin, right? 273 plus 27 is 300, right? So now we know T1 and P1, which is 30 over 300 equals P2 is 90 over T2. The reason we convert temperature alone to Kelvin is because of the 273 factor, which is massive. Okay, that's why we do that. So that, and then you take the 90 and divide by the answer. So that's 900 Kelvin. So 3 times, temperature will go up 3 times. All right, and that's how you do Gay-Lussac's law. And I got a practice problem for you. And this will be part of your my thoughts. Pay attention to this problem. It's a little tricky, but it's easier. All right, so stay tuned.